Hello! So today we are going to be learning about section 3.1, day 2, which is all about the connection between a derivative and a graph. Yesterday we started talking about how this thing that we've been finding, this instantaneous rate of change, is called a derivative. And we need to remember that the word derivative means slope of a graph at a single point. Remembering that and keeping that in mind will help us when we look at these graphs to make connections between the original graph, which we call f of x, and the derivatives graph, which we call f prime. If you think back to yesterday, so I'm just going to flip back in your notes packet, we learned that we can find a function that models the derivative. So we said that if we took the derivative of x cubed, the derivative function would be 3x squared. This function helps us calculate the slope of this graph anywhere we want. Using that information, we can kind of look at the graphs and how they would be connected to each other. So let's think about what we know about slope. If we look at a graph, the slope of the graph at any peaks, which we call maximums, and valleys, which we call minimums, are going to have slopes of 0. The reason that the slope here will equal 0 is because a line, a tangent line here, would just brush the curve. Now, how does that connect to the graph of the derivative? If we look down here at this same x value, so just go down on the paper, we'll notice that on the graph of the derivative, there is an x-intercept at each of those points. That is because the y value at that point would be 0. Now, why does this make sense? If this graph tells us the slope of this one, then any places where the slope would have been 0 are going to have y values of 0. Now for this next part, you're going to want to have like a highlighter, probably 2 different colors. So at this point in the video, if you don't have 2 highlighters with 2 different colors, you're going to want to go get them, pause the video, and then come back. So let's look at the slopes in another way. We know that the maximums and the minimums are places where the slope would be 0, so those would cause x-intercepts on the graph of the derivative. But what about the other places of the graph? If we look at all the places of the original graph where the slope is going uphill, so there's a positive slope on that section of the graph, and there's a positive slope on this section of the graph. So we call those positive slopes because they're going uphill. Let me see if I can find a pink pen. Here we go. Positive slope. Any sections of the original graph where the slope is positive are going to have positive y values on the graph of the derivative. So if you look at the derivative, do you notice that this first section of the graph and this end section of the graph are both above the x-axis? The y values here are positive, which means that the graph is above the x-axis. These 2 sections of the graph correspond to each other. Positive slopes on the original lead to y values that are above on the derivative. Positive slope on the original leads to a y value that is above on the derivative. Now what about that middle section? This is where you need the other highlighter color. This middle section of the graph all has a negative slope. It's going downhill. So this is all negative slope territory. Because this is all negative slope, the y values on the graph of the derivative would be negative. So if you look at this derivative graph, this section of the graph is all below the axis. Because negative y values would be below the x-axis. Now, when I'm asking you to analyze a graph, these are the three things I want you to look for. The first question you're going to ask yourself is, where on the graph are the maximums and minimums? Those should be x-intercepts on the graph of the derivative. Then you're going to ask yourself, where on the graph is the slope going uphill? Those should be sections of the new graph that are above the x-axis. And where on the graph of the original is the slope going downhill? Those should be sections on the graph of the derivative where the y values are below the x-axis. So what am I going to actually ask you to do? Like, what kinds of problems could I possibly give you? The first type of problem that I might give you looks like this. It's going to say, hey, f of x is given. So this is the graph of the original. And it's going to be really important in this class that you know exactly what graph you're looking at. So f of x is the original graph. You want to figure out the graph of the derivative. So how do you play the game? How do you play the matching game? The first thing I'm going to look for on the original are places where the graph has a maximum or a minimum. Now I've identified 3 places by putting points there where this graph has a minimum or a maximum. And since do you see the little arrow turns around and points back up again at the end here? That would be another minimum. Those are places where there should be x-intercepts on the graph of the derivative. So let's look at this graph. Is there an x-intercept at -2? Sure. Is there an x-intercept at a little bit less than 1? Sure. Is there an x-intercept close to 3? No. So this cannot be the graph of the derivative. Let's look at the next one. Is there an x-intercept at -2? Yes. Is there an x-intercept close to 1? Yes. Is there an x-intercept close to 3? Yes. He is still in the running. If we look at this graph, is there an x-intercept at -2? No. So this cannot be the derivative. If I look at this one, is there an x-intercept at -2? Yes. Is there an x-intercept close to +1? Yes. Is there an x-intercept close to +3? Yes. So we've narrowed it down to 2 possibilities. Then we look for all of the sections of the original graph that are going uphill. In this graph, this middle section here and this end section are both going uphill. So on my derivative, I'm looking for those sections to be above. In this graph, this middle section and this end section are above. But in this graph, the middle section and the end section are below. So this cannot be the graph of the derivative. Now, just to confirm that we've got it right, we didn't make a mistake anywhere, let's look at where this original graph is going downhill. So this original graph is going to have a negative slope for this beginning section and this section right here, which means on this graph we should be below in both of those sections, which we are. So there you go. That's how you kind of match. In this problem, you would say this is the graph of the derivative. Now let's take that same idea and see if we can match up all of these graphs to the graphs of their derivatives. Let's start with number 1. First of all, it says the graph of f of x is given. So we are looking at the original and we are trying to find the derivative. So in number 1, I notice there's a valley, a minimum at 0. The first thing I'm going to look for here is graphs that have a 0, an x-intercept, at 0. This one does not. This one does not. This one does, so he might be it. This one does not. This one does not. This one does not. So I really hope this is the winner. Now let's look at the slopes. This original is going down or uphill on the right-hand side. So we would expect to be above on the right-hand side, which we are. This original graph is going downhill on the left-hand side. So we would expect to be below on the right-hand side, which we are. That means that C has to be the graph of his derivative. Now let's look at number 2. I see that there's a minimum at the -1 and a maximum at the +1. So I need to look for a graph where there's x-intercepts at the -1 and the +1. A does not have x-intercepts there. B does not have x-intercepts there. D does not have x-intercepts. E does not have x-intercepts. F might. Now let's look at the slopes. We are going uphill in this middle section. So I would expect that my graph will be going uphill in this middle section, which it is. We are also going downhill at the beginning and at the end. So I would expect my graph to be below at the ends, which it is. F has got to be the winner. For number 3, I can see that there's a minimum at the -1, 2, 3. So I'm looking for a graph where there's an x-intercept at -3. This one has an x-intercept at -3. This one does not, this one does not, this one does not. So I really hope A works. We start off by looking at uphill. We're going uphill on the right-hand side, and we are above on the right-hand side. Then we look at downhill. We're going downhill on the left-hand side, and we are below on the left-hand side. So that corresponds, which means the answer is A. At this point, if you think you can try 4, 5, and 6 on your own, feel free to pause the video. I'm going to still walk through those, but let's see if we can match them up on our own. For number 4, I notice there's a minimum here. So I'm going to look for a graph where there's a minimum a little bit bigger than +1. So an x-intercept. No, no, yes. Now I notice I have a positive slope to the right of there, so I'm hoping that I'm above to the right of there, which I am. And I have a negative slope to the left of there, so I'm hoping I'm below on the left side, which I am. So the answer would be E. For number 5, I have sort of a minimum, but it's not curvy, it's a sharp corner. When there's a sharp corner like that, there's a sharp change in the slope. The slope on this side is a -1 the whole time, and the slope on this side is a +1. So I would expect that this side of the graph will be above and this side of the graph will be below. But I know there's going to be a sharp change, so I'm looking for a graph that has a jump in it. If you look at D, do you see there's a jump here between these 2 points? That's because there's a sharp change in the slope. It doesn't gradually change there. So we would look for that this side is above, and this side is below, which it is, and there's a sharp change in the middle, which there is a sharp change here. So this answer would be D, which means that B is the only option for number 6. If we look at the minimums and maximums, they do correspond. And if we look at where we're going uphill, it's in the middle. We're above in the middle. If we look at where we're going downhill, it's on the sides. We're below on the sides. So that should kind of make sense. All right, that's it for today. I'll see you guys tomorrow.